All right, guys. Hey, we're going to practice this first one here. If you would like to give it a shot before I solve it, I would say pause the video right now and try to solve this one. Otherwise, all these questions are found on the website, mrrast.com, and you can print them out and then double check your answers here. So if you'd like more detailed information on how to solve these, I'm kind of just going to jump in on it right now. Go back and watch the topic 11 kinetics video that I put, and I go through in detail on how to do this stuff here, in particular the third topic. So to solve this one here, we have to, the first thing we're going to do in all these rate law questions is identify what different experiments we're going to use to determine the different orders of these different reactants here. So I would choose, or I think you would too, we would choose experiment 1 and 3 for concentration A. And I would say I would do 3 on top because I noticed 3 is a larger number over 1. 3 over 1 because that's a larger number. And I would say 3.0 times 10 to the negative third over 1.5 times 10 to the negative third. To some power, that's the order of the reactant, to x to some power is going to equal, and again, I'm going to put 3 over 1, and I chose that so because it's a larger number and I just don't want to work with the fractions, over 0.6. Now in my head, I could pretty much see that these cancel with these. 3 divided by 0.5 would be 2 raised to the x power, and 2.4 divided by 0.6 is the same as saying 24 divided by 6, which is 4. There we go. So 2 to what power is 4? So that's second power. So that means A is a second order reactant. It's a second order reactant. Now for B, which ones would we choose to analyze? Which experiments would we use to figure out something that's changing on B? Again, why we picked A, 1 and 3 was because between 1 and 3, B didn't change. So for B, we want to find examples where A doesn't change. And so if we look at experiments 1 and 2, we can see A doesn't change, but B does change. Therefore, the change in concentration is entirely due to B. So we're going to choose this one, and I'm going to again put the larger number on top, and the larger number would be 1.2 times 10 to the third, because 10 to the negative fourth is even smaller. Remember, negative is small. So I'm going to put experiment number 2 over experiment number 1 when I figure this one out. So this would be 1.2 times 10 to the negative third over 1.5 times 10 to the negative fourth, and that will equal 4.8 over 0.6. And if you're not sure, you're not comfortable with these numbers, go ahead and calculate that out. So let's do that right here. 1.2 times 10 to the negative third divided by 1.5 times 10 to the negative fourth, and that comes up to 8. So this is the concentration 8 to some power. I'm going to say y because if I said x, it implies it's the same thing, and it's not necessarily the same answer. So 8, and then I have 4.8 divided by 0.6, and so 8 again. So the concentration went up 8 times, and the rate of the reaction went up 8 times. Oh, I didn't put that over there. So the concentration went up 8 times, and the rate of the reaction went up 8 times. So 8 to what power is still 8? That would be 1. That's a first order reactant. So this is a first order reactant. Now we know our formula. We just figured out the formula for this. And the formula is that the rate equals some K, some unknown constant. We're going to figure that out right now. Times the concentration of A squared. We just determined that A was second order. Times B to the first order. And I don't have to put the 1 up there. So I want to solve for K, and so K would be, if I cross multiply, I could bring this here down under the rate. So I could say K equals rate over A squared B, rate over a squared b. And then we just pick one of our examples, one of our experiments. We could choose any one. We'll get the same answer for k. I'm going to choose 3 just because I can move up my paper here and you'll still see 3. So let's try that. So k equals the rate of 3, 2.4 molarity per second. I'm going to put that in parentheses. That's the rate. And then on the denominator side, I have that a squared, which would be 3.0 times 10 to the negative third molarity, and that is squared. What's also on the bottom is the concentration of B, 1.5 times 10 to the negative fourth. And that's first order, so I just leave it like that. Okay, so let's solve that. Let's put these values in and see what we get. Let's see there. I would say 2.4 divided by, I'm just going to put it in simple, 3 times 10 to the negative third equals, another one, it's squared, divided by 3 times 10 to the negative third, and again divided by 1.5 times 10 to the negative fourth. And I've got a really, really big number here. If you have a scientific calculator, it's nice to just convert it over into science, and mine's this number here, but if you push mode or whatever your calculator is, I'm going to put in scientific calculator mode, and so that's 1.7, so I'm going to put 1.8, I'm going to round this off to 2 significant figures, times 10 to the ninth. And what's my unit? Units actually matter here. Oh, I forgot to put a unit there. The units actually matter here, so I'm going to say one of my molarities cancels. I'll just cancel this one out that I just drew. So what's left over? I have seconds, and I've got my molarities squared. So my answer is this over molarity squared seconds. And that's what my k is. So the rate law is both my value for k and, and my formula right here. So my formula and my value for k. So it's both of these things are needed for it. I need my formula and I need to know what k is, and that's the rate law for it.